My name is Dan Shumsky. I'm the author of the least action nuclear process model of cold fusion. It differs from other models that we've talked about this week and that have been proposed over the 25 years, and that the loading and the energy storage are looked at as reversible thermodynamic processes. In our quest for a cold fusion theory, we always have to be mindful of its boundaries. And I'm going to focus only on the third because the first two are quite obvious. The thermodynamic realities of the system. We're talking about a system that is thermodynamic in nature and temperature dependent. And as such, we would expect to have thermonuclear temperatures because of the transmutation events that we see in data from IICCF and others. The thermodynamic realities of this system are, it's first of all very far from equilibrium. Nuclear transmutations are occurring, but they're occurring at what appear to be room temperatures. There's no radioactive signature in our experiments, and the Coulomb barrier appears to be overcome. So the theorist has one question: what do we do with this? Let me take us through my view of this. When I see a system that is very, very far from equilibrium, and I've dealt with two of them in my lifetime, the possibility that it is a reversible thermodynamic process operating at the very limits of the second law is very real to me. Secondly, if we have nuclear transmutations occurring, we would expect the temperature of that system be at thermonuclear temperatures. I think that low energy nuclear reactions is really quite a misnomer. And the other two, there must be an explanation. I'll deal a little bit with these in my talk, but very briefly. But let us move on. The important question here is, how do you get thermonuclear temperatures in these devices? And I would propose to start by with Max Planck's description of temperature in his 1909 lectures in Columbia University. Paraphrasing him, would say that temperature is a derivative. And if we take a look at the temperature under any of the, where is this? There is a pointer here. Under any one of his steady state black body spectral curves, the area under that curve defines a unique temperature, and the temperature is not dependent in any way on the material, but it is, and also not dependent in any way upon the size of the particle. And I'll talk to that a little bit later. The units that we're talking about, since this is a derivative, are joules per time. Since we're dealing with a system that is so far from equilibrium, we have to get away from Planck and his equilibrium distributions. In fact, what we have to do is to coalesce Planck's theory of heat radiation with the theory of Maxwell, Boltzmann, and who described heat as the molecular motion of particles in an ideal gas. Let me talk about the division of heat energy into two domains. One is the domain that's characterized by molecular motion. This is the revered names of Maxwell and Boltzmann are associated with it. There is a temperature associated with that, T sub m, which is the thermodynamic temperature that we use in physics. The other domain is the radiation domain. It differs from the first in that all of the energy is locked in electromagnetic radiation. It has a temperature characteristic that we're going to describe as T sub r, the radiation temperature. And these two temperatures at equilibrium are identical, but I'm going to take them to very far from equilibrium separations because we are dealing with a very far from separation, far from equilibrium event. I'm showing in the slide the direction of the entropy increase from the relatively organized radiation structure to the very disorderly random motion of molecular particles. We'll start with Planck's black body distribution, his equilibrium distribution at essentially 20-25 degrees, or in our case maybe up to 60 or 100 degrees for our cold fusion reactors. And we're going to first of all keep this substance at that temperature with mass domain radiation, or mass domain energy alone, as you might get from friction, and this might be the initial condition after one has created an increase by friction. You see the number of quanta at each frequency increases quite dramatically. You know, it can be quite dramatic for this initial condition, but this is all going to decay down to a new equilibrium where the mass and radiation domains are in equilibrium. You'll also notice that the Wien frequency has not changed during this translation. In a similar fashion, we can change we can keep the object by radiation domain input, as from the sun or some other radiation source. And what we see here is that the Wien frequency, okay, the frequency associated with the radiation temperature, moves to the right, and what we add is a lot of energy to the right of the initial curve. This is very high energy quanta that are being added, and we will see that we begin to approach solar core temperatures in this way, as long as we can keep it in a stable, far from equilibrium condition. So let me just very quickly review here the radiation heating, see the mass domain heating, and then the two of them together is giving us Planck's equilibrium distribution after these have equilibrated to a new equilibrium condition. I want to let's just go back to that for a moment. The equation that describes this non-equilibrium or far from equilibrium black body radiation condition is a transfer function. And it is a transfer function that takes gamma photons, very high energy gamma photons, into the black body spectrum and then redistributes them as very low energy heat and RF or UV and even soft X-ray photons. And let me just very quickly take a look at that. If you have a gamma emission into this system, if the gamma frequency has if there are vacancies at the gamma frequency, the gamma is just absorbed into the far from equilibrium distribution. But if it's not, then the gamma is still absorbed into the black body distribution, but its energy is dissipated to the left into low energy frequencies. It's the same kind of thing that happens when you heat a cup of coffee in a microwave at relatively high energy. When you take it out, you have relatively lower energies in the system. So let's take a look now at the radiation storage of energy, because that's where I'm going to be dealing almost exclusively during my presentation. And let's increase the radiation domain energy, but do it while we keep the thermodynamic temperature exactly constant, okay? And what I'm showing here is that you can achieve very high concentrations, or very high temperatures, but where are those temperatures isolated? That is really the key element here. And I'd like to begin by talking about the QED description of a covalent bond, which I'm sure that you're familiar with, where an electron it emits a photon, H nu. It is absorbed by the covalent electron, and then re-emitted, and absorbed by its covalent electron. This is a completely reversible thermodynamic process. The energy is conserved, and there is no change in the overall entropy condition of the system. This is what keeps this building standing. It's what keeps us together and functional. These bonds can go on for very long periods of time until they are disrupted. Now what I'd like to suggest to you today is that the same kind of thing might happen between nuclei. In Mossbauer resonance, in other words, the gamma photon is absorbed and emitted by a nuclei, and its covalent nuclei is absorbing and emitting the energy as well. The emittance is given by the energy h nu. Okay? The photon energy in that gamma that's being exchanged at a distance of one wavelength. And the temperature, remember our derivative? The temperature is the energy multiplied by the frequency with which it's occurring, divided by 2 because the emittance is only taking place in either of these 1/2 of the time. So notice how the temperature is going up now as nu squared. So as we get into higher and higher photons that are supplying the force, okay, this is electromagnetic force, one of the two forces in nature, that is keeping these things together at that particular distance, at the one wavelength distance. Solar temperatures might become possible. Let me go on. If I can go on. Well, I want to emphasize or bring back and make sure you understand 2 points. The first is that the energy is stored between subatomic particles. There is no external manifestation of this kind of energy storage. It is strictly between the nuclei. I don't know of a way that it can be measured, and I will come back to that a little bit later on as a challenge to the experimentalists in the room. How do we measure such a thing? But you can get these enormous energies, and also, how do I do this? Also these extraordinary temperatures, because now the temperature of the process is locked between subatomic particles. So in this room temperature device, we now have temperatures that are in the solar core, or possibly even in the stellar nucleosynthesis range. So let's take a look at some of the consequences of doing this. We take a look at deuterium fusion. We're talking about distances in the picometer range. We're talking about temperatures that are about the solar core, and deuterium fusion can take place under those conditions. These are conditions now that are existing within the electrode. But what's more important, and if you are to believe the experiments of people like Miley and Mizuno, where they have these very high atomic weight products being produced, we're seeing distances as we increase the gamma intensity between these nuclei up in the femto range. And all of a sudden it becomes possible, and I'm sorry the RNS processes are transposed here, but it is possible that one could get nucleosynthesis processes in this device because you now have the temperature conditions and also the distance conditions that are required. Let's take a look at another consequence of this. And here I'm showing the Rossbauer resonance between two nuclei, and I'm also showing in this graph over here the temperature of the process. These are not measurements of any sort. They are more illustrative than anything else. But watch what happens as I increase the radiation, the temperature or the energy of the gamma. Number one, point in that direction. The distances are becoming smaller because the energy, the electromagnetic force between the nuclei becomes greater. The temperature is becoming greater, and ultimately what you end up with is, I believe, the possibility of cold fusion. So what we have done is we've identified the temperature that can be localized in the system that is in the range that we need to produce these very heavy nuclei. We have proposed a method of bringing the nuclei close enough together using a standard QED method or a model of the electron. What we've done is we've added two parts, two elements of physics here. One is the non-equilibrium or far from the equilibrium theory of heat. That was something that I worked out 25, 30 years ago. I started working on it 40 years ago before this group ever existed. But it finds a very suitable application here. Is this thing possible? What I would like to do is to challenge the experimentalists in this group to measure, before the experiment, at the point where the experiment is fully loaded, and at several points during either excess heat or even no excess heat experiments, the amount of energy stored between nuclei in the surface of the electrode. Mossbauer in his experiments, if you go back and you read his Nobel address, he talks about this very, very wonderful experiment he did. It was the last paper it was the last paper published in the German language in the scientific literature. But in his experiments, he witnessed these extraordinarily high temperatures, this emission of gamma radiation. But what he hasn't done is, what I've added is the second part that we've added here in terms of science, is the nucleus in close proximity to the first, which absorbs the Mossbauer resonant photon and then re-emits it back and forth. So he didn't carry the understanding far enough, but he didn't have to. I do. Let me go to one other consequence of this, and that is, and this may seem like a very small point to us, but I think it's important anyway. As the distance between the nuclei and the surface of this electrode become smaller and smaller, we're putting a lot of tension into the surface layer while the bulk is remaining relatively unaffected, and the effect is surface cracking. So I'd like to invite you to read a little more at my website. There's a video that explains the LAMP theory in quite a bit of detail, and I'd like to ask if there are any questions of me. It's an exotic theory, I know. Yes.
I'm always fascinated when people talk about Fermi-sized objects in the context of surfaces where the chemists are operating at angstrom sizes. I wonder if you could sort of help me figure out how to think about a crack when I've got length scales that are different by 10 to the 5th.
Well, if you have those length scales occurring only in the very surface layer, I can describe it. Let's say you take a balloon and you put plaster on it, and we're going to go in the opposite direction and instead blow the balloon up. You're going to get a lot of tension in that surface. This is the opposite. As the nuclei become closer, there sets up a lot of tension in the surface of the electrode that's not present in the bulk, and the result could be surface cracking. And we're talking about these distances. We're talking about, we know that the Coulomb barrier is overcome. We know that thermonuclear reactions are occurring. The thermodynamic realities of this system should focus our attention on figuring out why those things are happening. The other question? This is a beautiful hall, isn't it? It's such a magnificent place to give a presentation.
Okay, if I remember well, the Mossbauer effect, if you take in account the time for the Mossbauer effect between all the nucleus indicating, the time of transition must be lower than the speed light time. In fact, the Mossbauer effect does not can explain by punctual interaction between two nucleus. In fact, it involves ensemble of nucleus, like big amount.
Well, we're not in any way altering the speed of light between these two.
Okay, but if I have understood, you say that there is an interaction, maybe like a gamma.
Morse power resonance between the nuclei, yes.
A field agent between the two nucleus. But this gamma should be speedier than the speed of light to explain this. In fact, the Bauer effect is incredible because there is not this interaction. So every interaction, that's the talk before of this, speaking about punctual interaction between two particles, is impossible to, is in contrast with the speed of light. You are in the wrong domain of space-phase.
Yeah, we're not doing anything to alter the speed of light. The reason that things occur quicker there is because the frequency has increased.
I'm speaking about the time of transition between this interaction between these two nucleus, two new particles.
Yes. And why do you say that it is, I'm operating at greater than the speed of light? I don't understand that. Because I've looked at this.
Okay, the question is this one. If you do not take in account a model with a coherent field, you are not able to explain Bauer effect. In fact, Professor Giuliano Preparata, he explained in his coherent model the Bauer effect, and it's demonstrated that the Bauer effect cannot be explained with particle interaction, mutual particle interaction between two particles.
I understand that.
If you are out of a model speaking about coherent field, you have no explanation, or you have absurdity speaking about Bauer. It's the same of the talk before of this with the other professor. So, if you do not take into account a coherent model involving thousands or millions of particles like Bauer effect produce,
Yes.
you have inconsistency in physics. Okay, this is my question. Thank you.
Thank you. So I have a chance.
Excuse me, you can discuss about this difficult physical question in front of the poster, maybe.
Yep. I understand what you're saying about the interaction between the two nuclei. This is the second element of new science that I'm introducing here, and I do certainly appreciate your interpretations and criticisms of it, and it gives me something to go back and look at. So thank you.